problem, right? Just in the case that sometimes the information, like that, if you remember that we have the assumption that for the linear programming about the certainty, we assume that we know all the information with certainty. But sometimes, even though we assume that we know with certainty, but okay, when we finish the analysis and we're gonna make the decision, some information might be changed. Right? For example, let's think about during the way that you analyze the problem, you're using the cost per unit is around, let's say, $200 per unit. And then you analyze using the linear programming, you get the result, right? You're gonna make the decision. But the government is, change the policy, right? They increase about the wage of the workforce, right? So it's gonna make that the unit cost might be changed, right? So in this case, we need to study how it affects to our optimal solution. So in conclusion, we will study certainty analysis because sometimes we have the uncertainty with the linear programming model because some information might be changed. And the way that we analyze about this topic is that we try to explore that, okay, what will be the effect to our optimal solution? Okay. So in this case, it means that for certainty analysis, the first thing that you need to keep in mind, we can analyze the certainty analysis just only you get the optimal solution already. So it means you need to have the optimal solution first before you analyze the certainty analysis. Right? And the certainty analysis is allow you to not recalculate. You can know all the effect to the optimal solution, but we require the change of the parameter just one parameter at the time, and the rest is going to be the same. So if you analyze a problem that you change the parameter 2 or more at the same time, it is not the certainty analysis, it's a new problem. You need to recalculate everything. For example, you might analyze the certainty analysis in the case that the raw material increase, just only one, and the rest of the parameter is going to be the same. But if you have the raw material increase and also at the same time you have like labor hour increase as well at the same time, this is the new problem. We cannot analyze using the certainty analysis. We need to recalculate, right? So this is the condition. First, certainty analysis, we do it after we have the optimal solution. Second one, we allow the change just with one parameter at a time. Okay. And the approaches that we will use for certainty analysis, okay, we have graphical, we have simplex method, and using the software program. As I mentioned last time, simplex method, we will skip it, we are not studying because this is the algorithm in the computer programming. So in our class, we will study just only the graphical method and the software program, like the computer output. And for today, we will use the graphical method to do the certainty analysis. That will be the foundation of your, reading the output from the software program, right? So if you do understand information today, when we study, right, using the software program, including the Microsoft Excel, QM4 and other program to solve for the linear programming problem, you can have, right, very easy, right, to read and understand about the printout of the output from the program. So today is very important. It's like the foundation, right, for the software program. And before we do the certainty analysis, firstly, you need to understand the terminologies. So I have around 3 terminologies that you need to understand before I teach you about what is the certainty analysis gonna do. The first terminology is about, decision variables that we have 2 types. We call basic and non-basic variable. Basic and non-basic variable. And all the information actually in the slide already. Basic and non-basic variable, actually, basic variable is mean the variable that you have the value is not 0, right? Not 0 value, we call basic variable. And if you have the variable that have the 0 value, we call non-basic variable. So basic variable, non-zero value. Non-basic variable, it is about zero value variables. For example, you solve for the linear programming and finally you get in the result x1 equal to 3 and x2 equal to 4. Both are not zero, so both are basic variable. But if you have, let's say, x1 equal to 0 and x2 is 5, x1 is non-basic variable and x2 is basic variable. Okay, so detail in the slide only. So this is the first terminologies, basic and non-basic variable, the first set. And the second one is about, okay, objective function value, you know about, this is the z value, you know about this already, right? It's about the total profit or total cost, for example. But another term that you need to understand is called slack and surplus. Slack and surplus. Slack and surplus is tell you about amount of resources, right, that you actually use compared to available that you have. Right? So for slack, it means your resources that you use is less than available that you have. So you can imply that you have the remaining resource. This is a slack. Slack is about the remaining resources. Surplus is on the other hand, right? It is about the actual resources that you use more than the minimum requirement. Okay, so the amount that you use more than the minimum requirement we call surplus. I will show you about the explanation via the example using the calculation in the next few minutes. So why do the slack and surplus is quite important? Because if you understand slack and surplus, you can know that okay, your resources is now you have remaining or not, and then you can know that okay, what you can do after that, right? In the case of safety analysis, if you have remaining, if you don't have the remaining resources. So here's an example for slack and surplus. Let's say that okay, I have one of my constraints, right? I'm gonna use the constraint from the example of Fair Furniture Company last week. Let's say this is one of my constraints. I have 4x1 plus 3x2 less than or equal to 240. And 240 is about the level out, right? Remember? Okay. And assume that I'm solving using the linear programming. And finally, an optimal solution. An optimal solution. An optimal solution, I have x1 is 30, x2 also 30. So, if you substitute x1 to the left hand side of this constraint and x2 to the left hand side of this constraint, you're going to have 4 multiplied with 30 plus 3 multiplied with 30 less than or equal to 240, right? And finally here you have like 210. It's okay. What is the meaning about this? It means that okay, finally at optimal solution, in order to have maximum profit, let's say you're gonna produce x1 30, x2 30, and amount the labor hour that you're gonna use is 210 hours. You have available 240 hours. That's fine, right? You have available 240, but you're using actually 210. This is the one that you actually use. So finally, what happened here is different is about 30 hours, right? This one is the remaining. Remaining labor hour.
Yep.
So we call slack. You use just 210 at optimal solution. You have available 240. Right? You have remaining 30 labor hour. 30 labor hour is the slack. Okay. So the way that you calculate it, just substitute the value at optimal solution to the left hand side, and then you can find the result. On the other hand, if I have another case, let's say that I have constraint is 2x1 plus x2 greater or equal to, let's say, 70. Let's say this is a minimum requirement. Let's say this is a requirement. Maybe you can think about now you're gonna make the supplements food or something, and you need at least 70 grams of vitamin A, let's say. So 70 is minimum requirement because your constraint is greater or equal. So let's say that at optimal solution again you have x1 30, x2 30, suppose that. Then you substitute x1 to the left hand side, x2 to the left hand side. What do we have? You have 90, right? So at optimal solution, the actual one of these resources that they use is 90. But minimum requirement that you need is just at least 70. That's okay, right? You need at least 70 and you use 90. But the difference from this is about 20, right? This 20 is about the resources that you use more than the minimum requirement. Now this is called surplus. So the way that we calculate surplus and slack, we just substitute value at optimal solution to the left hand side of the constraint that we considered. Okay? And then you can see one thing. If you have constraint less than or equal, you probably have slack. If you have the constraint greater or equal, you probably have the surplus. Okay? So this is the surplus and slack, the explanation. So this is the second terminology. It's the slack and surplus. Okay? And another one is that, okay, you're going to have binding and non-binding constraint. Don't worry, all explanation is already in the slide, right? If you get it, it's nothing more than this. But this is the actual one that we have. Okay, let's talk about the last terminologies. The last set is about binding constraint and non-binding. Okay. So what is binding constraint? Okay. Suppose that I have this example. Let's say that I used the example last time. Remember, we have the example of the fair furniture. This is last week information. We analyze this problem, and finally we have to resolve optimal solution occur at point C. And at point C, we do have the coordination x130, x240, right? So it means that if we want to get the maximum profit, you produce x130 unit and x240 unit. One thing that you can see here is that at point C is optimal solution point. And this point is occurs from the cutting point between constraint 1 and 2 cutting together. So binding constraint is the constraint that cutting together and provide the optimal solution point. In this case, constraint 1 and 2 both are binding constraint because it's cutting together and provide the cutting point to be the optimal solution point. Okay? So binding constraint is a constraint that provides you the optimal solution point. Right? Because it's cut together, provide the optimal solution point. This is binding constraint. Okay. And based on the foundation of mathematics, if this two is binding constraint, you look at this, at point C is optimal solution, x130, x240, right? If I try to find slack or surplus, let's say in this case we have less than or equal, probably slack. I substitute x130, x240 to the left hand side of this constraint, binding constraint. What happened? 30, 40. You have 240. 30, 40, you're going to have 100. It's probably equal to the right hand side. Yes, for sure, because this is the cutting point. Right? And you using the coordination of cutting point, substitute to this equation, probably is equally. What does it mean? There is no slack and surplus in this case. Okay. So it means that binding constraint, we have no slack and surplus. Right? Binding constraint, no slack and surplus. Binding constraint, there is no slack and surplus. in the business context, if you don't have slack or surplus, it means that you use all the resources that you have, run all. For example, in this case, you have available currently level out 240. At optimal solution, you use all 240 that you have. Pending level out, you have over 100, right? So at optimal solution, you use all 100 you have. You don't have any remaining. So this is binding constraint. Okay? You don't have slack surplus. Binding constraint, no slack surplus. And what is the thing that's more than that? You can see another one. This one, if you confuse, that's okay. I will explain using another example, but I just want to explain you a little bit. It's that if you try to relax the constraint, right? For binding constraint, you're gonna getting the result that getting have an improvement or getting better. The result or the solution is getting better. For example, if your problem is try to maximize the total profit, it means you have more profit. If you have the problem that you try to minimize the total cost, the result improved, it means you have the lower total cost. Now look at the word relaxing the constraint. What is it? Relaxing constraint means that you try to relax the constraint by have release about the limitation. For example, if you have the constraint that have the signal less than or equal, look at this, less than or equal. Suppose that I use the example last week. Once again, I have this is like a solution. Look at the first constraint. The first constraint for x1 plus x2 less than or equal to 240. The constraint is has signal less than or equal, right? If you try to relax the constraint, you try to release about the limitation of this. How can we do that? Less than or equal is mean on the right hand side is available resource that you have. You cannot use more than the right hand side, right? But if you want is more relaxed, the term relaxing constraint means you try to increase the right hand side. You can give more resources. For example, in this case, if you want to relaxing this constraint, it means that you try to have more level out than 240, let's say 241, 242. This is the relaxing constraint for less than or equal constraint. On the other hand, if you have this constraint is greater or equal, the right hand side is the minimum requirement, right? So if you try to relaxing this constraint or release about limitation, I try to reduce the right hand side. This is the word relax. For example, I said that okay, if you want to getting an A for this course, you need at least 85. But if I want to you more relaxed, I said okay, not 85, maybe 80. Okay? So constraint greater or equal. Relaxing constraint, you try to reduce the right hand side. So in conclusion, for binding constraint, if you try relaxing the constraint by reduce the right hand side for constraint greater or equal, or increase the right hand side for constraint less than or equal, you will have the better solution. Better solution, as I mentioned, in terms of total profit, you're getting profit getting higher. In terms of total cost, you have the total cost getting lower. I will show you based on the example in the next few slides. But for non-binding, we have another one we call non-binding constraint. For non-binding, it's on the opposite side. First, this is a constraint that not help anymore, not provide the cutting point for the optimal solution. For non-binding. And for sure, if you try to find the slack or surplus, you're gonna have it. You substitute value at optimal solution to the left-hand side of non-binding constraint, you're gonna have slack or surplus for sure. And if you try to relaxing non-binding constraint, you will not getting the better result. Okay, you will not getting the the better result. Okay, so this is the terminology: basic and non-basic, select and surplus, binding and non-binding. Okay. During the time that we're waiting for the handout, I'm gonna use this example to explain you as a review. Look at this. This is the linear programming model. We know that. Today, as I mentioned, we're gonna study the safety analysis. For safety analysis, we're gonna have two parts. The first part is analyze just only for the objective function. And for the objective function, one variable that we allow it to change is about the coefficient in front of x. So unit profit change, unit cost change, something like that. This is the first part. The second part for safety analysis is that we're going to analyze the constraint. And if you remember, I said last week for the constraint, on the left hand side, this is a fact. You cannot change, right? You cannot change. As I mentioned, okay, if you want to build this one screen, you need 10 volts. You cannot say, okay, I want to change it to be 9 volts, and you cannot do that. This is a fact that you need to use intent. But one factor that we can change for safety analysis is about the right hand side of the constraint. Amount of resources. You change the number of raw material, you change about the number of labor hour, you change the number of material, you change about the capital that you have. Okay? So this is the second part. First, change the coefficient. Second one, change the right hand side of the constraint. Okay, and look at this example. Okay, the example is about the Stratton company. This company produced the plastic pipe, two types of pipe. It requires 3 resources: extrusion hours, packaging hour, and additives material. The following data shown in the next slide is about the next week situation of this company. All the data are expressed in the unit of 100 feet long of pipe. For example, if you try to produce 100 feet long of type 1 pipe, you require 4 hours of extrusion work, 2 hours of packaging work, and 2 pounds of additive mix. If you try to produce 100 feet long of type 2 pipe, you require 6 hours of extrusion, 2 hours of packaging, and 1 pound of additive mix. And right now, you have available extrusion hour 48 hours, you have available packaging 18 hours, and you have available additive mix 16 pounds. Furthermore, you know about the unit profit, let's say. The unit profit per 100 feet long of type 1 pipe is $34. The unit profit per 100 feet long of type 2 pipe is $40. So now we would like to analyze this problem using the linear programming. And we want to know that, okay, how much of each pipe that we need to produce in order to getting the maximum profit. So it means that if I want to solve for this problem, firstly, I need to determine the decision variable. And for sure, in this case, we all know that decision variable we have x1 and x2. x1 is probably amount of the type 1 part that we're going to produce, and it should be expressed in the unit of 100 feet long. x2 is for type 2 pipe. And for sure, I said expressed in 1 per 100 feet long, so it means if you solve that x1 equal to 2, practically it means you're going to produce 200 feet long. If you analyze x2 equal to 3, let's say, practically you're going to produce 300 feet long of type 2, something like that. And based on all the information of this example, this is the linear programming model. Our problem right now, we try to maximize the total profit, or Z, equal to 34x1 plus 40x2. Subject to, we do have 3 constraints. 4x1 plus 6x2 less than equal to 48. This is the extrusion constraint. 2x1 plus 2x2 less than equal to 18. This is the packaging constraint. 2x1 plus 1x2 less than equal to 16. This is the additive mix constraint. Okay? And nothing much. we using the knowledge from last week. We're gonna solve it using the graphical. If you still remember, we have 3 main steps, right? The first step, we drawing the graph of all constraints. The second step, we try to find the intersection area, we call feasible area. And then we substitute the value to be the total profit and draw isoprofit line. And then we projected this isoprofit line to find the optimal solution point. Finally, this is the solution. This is solution. Based on this example, you can say, this is a graph of all 3 constraints. In this slide, feasible area is area of A, B, C, D, E. This is a feasible area, or intersection of all constraints. I just substitute total profit to be 272, and I have this graph, the dashed line is my isoprofit line. So and then I use a ruler, remember? Cover the line, maximization. So I need to project in the direction that out of origin point. So then I project this. And the last point of feasible area that I can contact using this isoprofit line, before the isoprofit line out of feasible area is this point C. This is optimal solution point. And at point C, what is this? This is about the cutting point between packaging constraint, cutting with the extrusion constraint, or constraint 1 and constraint 2, cutting together. So I'm doing the mathematical things, find the cutting point between these 2 constraints. And I have this coordination at point C, optimal solution, x1, 3, x2, 6. Okay, so what can we have here? It said that, okay, if you want to have the maximum profit, you need to prove x1 equal to 3, x2 equal to 6, okay? Or practically produce type 1 300 feet long and type 2 600 feet long. You're gonna have the total maximum profit. And if I use this example to make all the review of all information that I'm just tell you today, what is this? Firstly, at point C is optimal solution point. We have x1 3, x2 6, right? x1 and x2 is not 0 value. So we call x1 and x2 basic variable. Because it's not 0 value, we call basic variable. Second one, at point C, or the optimal solution point, is this occur from the first constraint, extrusion constraint, cutting with the second constraint, packaging constraint. So packaging and extrusion are binding constraint because it provides point C, optimal solution point. On the other hand, look at additive mix constraint, this one. This constraint right here is not cutting at point C, right? So it not provide the optimal solution point. So additive mix constraint is non-binding constraint. Okay, this one is non-binding. Next one. If you look at point C, optimal solution x1, 3, x2, 6. If I try to substitute x1, 3, x2, 6 to the left-hand side of packaging constraint and extrusion constraint, this binding constraint, right? You're gonna have this one 18 equally to the right-hand side. You're gonna have this one 48 equally to the right-hand side. We don't have any slack or surplus for packaging and extrusion. So it means practically we use all the 18 packaging hours that we have, and we use all the 48 hours of extrusion that we have in order to have the optimal solution. But if I substitute x1, 3 to 6 to the left-hand side of additive mix constraint, which is non-binding constraint, x1, 3, x2, 6, you're going to have 12 on the left-hand side. But you have available 16. What does it mean? It means that at optimal solution, you use just 12 pounds of additive mixed material. But you have available in your warehouse 16 pounds. You have remaining 4 pounds, right? That 4 pounds we call slack. Okay, we call slack. So, this one, right? Additive mix, we use just 12, we have available 16, we have remaining 4, 4 is slack. Why is called slack? Because it's less than or equal. Less than or equal. is slack. The next one, how about the way that we relax the constraint? Okay, I will use the example from packaging constraint first. Look at this constraint. Packaging constraint, cutting at point C, right? It provides optimal solution point. We all know that packaging constraint is binding constraint. Let's say that I'm trying to relax this constraint. This is less than or equal, right? So I try to give more right hand side. For example, if I have more packaging hour, let's say 19 instead of 18, what happened? Original problem we have 18 and we have no slack, no surplus. So we use all 18 that we have. If I change it, I add it one more hour, we have 19, what happened? We can expect that we can produce more. Because 18 we use all of them. So if we add one more hour, we can expect that we can produce more. If we can produce more, we can have more profit, right? But on the other hand, look at additive constraint. This is non-binding constraint. If I try to add in one more on the right hand side from 16 to be 17, it doesn't help anything. Because at original problem, we have 16 pounds and we have used just 12. We have 4 pounds remaining. If you add one more pound with 17, it doesn't help because you can still use 12. Okay? So this is why I said that if you try to relaxing the constraint, binding constraint, you can expect to have improvement of the result. In this case, you can expect to have more profit. But for non-binding, in this case, additive constraint, if you add more on the right hand side, it doesn't help anything. Because first, you still have 4 pounds remaining. You add one more, you have 5 pounds remaining. Doesn't help. You cannot expect that you're going to have the better result. Okay. So this is the not something as it yet. Just explain about the terminology of binding, non-binding, basic, non-basic, slack, and surplus. Okay. So I don't want to go further more than this because the next one I want you to have the handout. But before we move on and getting the handout, we're waiting for the staff. Any questions for now? No? No question? Really? Okay. Well, good question. Okay. No question? Sure? Yeah. You can have.
So we read there's a presentation coming up, and we don't have a group yet. So probably it's not a we try to make it possible, but is anybody looking for members? We don't have like a group yet.
You don't have a group yet? Okay. Okay. Good. Last week, did you come last week? Sorry, did you come last week? No. No. You did, as I remember you. So, yeah. Okay. Okay. Let's see.